Okay, so the session is, of course, being recorded. And so, Linda, can you go to the first slide, please? Or next slide. Okay, I'm going to talk just a little bit. There's a bullet point that's called Linda. And Linda, this is your opportunity to say anything if you want to. Before that, what we're going to be doing is we will do a little poll about wellness, just how are people, and I don't mean necessarily physically well, although, I hope everybody is physically well. I'm talking about relative to the course, what we're doing and where we're going. And let's see, and so on and so forth. Okay, so let me get at the very top then. I'm just reading to you, but these are announcements. I want you to pay heed to them, please. Hey, Josh. Okay, so it is finally today, the last of the accommodation scheduling for the midterm was resolved with the students involved. This happened about an hour ago, and I've spent all day on this, actually. Okay, you should be happy to know, though, that everyone was accommodated, and that means that no one is scheduled to be on tomorrow, so that means that everyone was accommodated, no one was hurt, no one was disadvantaged. So that's kind of our watchword during this COVID period, as it should be, I think. That means that grading can now ensue early tomorrow. But what I'm telling you is don't worry about that. Focus on your physics. Everybody will be fine. Individual emails will be sent with your midterm status. So if we had a Susie Smith, we don't, but Susie Smith would get an email from me, and it would just say, hey, Susie Smith, here's the deal. And that's where you are now, and so on and so forth. Everybody rest assured you will be fine. And Linda, this next thing is maybe more of a question. I don't even know. But I get these emails from people saying, oh, where's this at? And things like that. Now, I'm guessing, and I'm not being mean to them or anything, but I'm guessing that they just haven't read it and they're notified through the announcements or somewhere where these are. And I also realize that we could just say, hey, go to the YouTube and find it there. But are these postings happening in the announcements and things like that? And I'm not really even asking you now. I'm just saying, let's make sure that they are, because I'm getting these, emails from people, and I just want to make sure I can say, hey, it's in the announcement. So that's
okay. I'll post a link to the playlist in the announcements.
Okay, great, thank you. And you can be me when you do that if you want, or you can be yourself, whatever. As long as they're posted there, that's good. Okay, now I am keeping all of my office hours, and it's okay because I can do work if people don't show up. But actually, someone showed up today, and it was a very good session. I think they benefited from it, and we went through some of the vector stuff. But they said that vector stuff was a little bit quick. Could we do a little bit more? So I changed what I was going to do today, and Linda and I are going to be doing a little bit more in this period. And Linda, the thing I talked to you about, there's nothing I'm going to be asking you to do relative to that. I think I'm going to be able to use the advice you gave me. Oh, and Abby, those links are going to be posted in the announcements. Okay. All right. So, I think we're maybe down to polls. So, Linda, could you throw up something about, how are you and things like that, and we'll find out how many people are here and so on and so forth. So, go ahead, please. Sometimes I have to think too for a while as to how I am. I do. Or actually, I'm really thinking about what do I want to tell people, not how I am. I actually know that. Okay, So, you know, we're kind of spread out. There's a lot of OKs, and OK isn't bad in this day and age. There's a couple of grades. If you are struggling, you know how to get help, okay? Linda is certainly has you know, availabilities. I have availabilities. Tom Topol has availabilities. So help is there. Turns out none of that stuff works. Contact me, and we'll figure something out. Not in this class, but actually in another class, I ended up spending quite a bit of time with a student. I think it was time well spent, though. And I followed up with that student today. I called them and I said, okay, so now how's it going? He said, you know, it's really good. And I think I'm changing my life around, so I'm going to be able to come to some of these things and maybe, you know, not have to catch up in a hurry. So that's good. And so thank you for that participation. Linda, anything you want to say?
No, if what we discussed earlier is good, then I think that takes care of it.
All right, that's good. Thank you then. Okay, we're not trying to be mysterious. It just that's something we don't even need to go into here. Okay, I'm throwing this open if there are questions and answers out there. Now, everybody realized I already told you where midterm stuff was in the first part of this. So unless you've got more questions about that, and certainly we can ask them, but I did cover some of that stuff. So any questions laying out there? You guys are all too young to know this, but once upon a time when I was a kid, and I still listen to this music sometimes, there was a song called Sounds of Silence, and that's exactly what I heard there, so that's okay. So we're going to go into physics, and so we're going to actually do a whirlwind tour of the appendices. I just want to show you what's in the back of the book there, and then we'll talk about vectors, and we'll actually talk about more things than vectors. So Linda, we're going to do a whirlwind tour of the appendices. So Linda's going to change the channel, and we'll see Appendix A. Now, there's a French outfit, and I don't know if Linda's going to choose to point at that or not. Can I point?
You can.
I will. I would just point. I will not try to make you point. Okay, so we'll go here. This is a standards outfit that worries about units. And so they worry about units of length, and they also worry about what really is the definition of these. It's a French outfit. And so usually when they're talking about this, they'll call it SI units, even though they call it International System Units. And the reason that's in different order is because that's how you do French.
But I think you got to click on the pointer. Next to the little icon that looks like a mouse.
All right. Okay. So I'm here. Can you see me or no?
No.
Huh.
It looks like a little finger in the top left.
Oh. All right. This one.
There we go.
Okay. Now you can see me. All right. I was actually clicking on something else, but I thought it would work, but it didn't. Okay. So in French, they just put the adjectives in a different place and things like that than we do in English. But they worry about what is the unit of length, which is a meter, the unit of mass, which is a kilogram, the unit of time, which is a second. These are other units that we could talk about. Actually, to tell you the truth, in this ultrasound physics we're talking about, we're not going to talk about much of that. But anyway, these units are in Appendix A. Let's go to the next slide, Linda, and this is Appendix B. And, you know, I'm asking you to do that. I really can do that myself too, can't I?
You can.
All right, great. See, I'm getting more and more efficient here. This is the Greek alphabet. And you might say, I don't care about Greek alphabets. Well, and maybe that is true, but these letters will find themselves into your formulas. Now, some of them you already know. For example, mu was down here, and you know that from before, and mu will have a different meaning in this part of the course. You also know about sigma, because that was standard deviation, but now it's going to be used for different things. So there's a whole bunch of these Greek letters that are here. This tells you how you pronounce them, and so on and so forth. So those will come up in some formulas. I'm going to see if I can do this. Now, you might say, why did I skip Appendix C? Appendix C is the periodic table, and that's really extremely relevant in chemistry, not so much in the course we're going to be doing. But here is unit conversion factors, and we're doing this tonight. And you would be given these kind of things. So, for example, if you wanted to change a centimeter into an inch, it would be up here, and that's what you would be looking at. And E is some numerical constants, like the speed of light and so on and so forth. Now, there will be problems that we will talk about where we'll have to go and get these things from the tables, and so these would be provided if we get around to having a and we will get around to having a final exam. These things will be provided in the grace notes. Still, you want to know, they're there, and if you're using the book. In fact, Linda, let's just do another poll. Again, I don't know who you are, and I, in one sense, don't care. I'm going to ask anyway. How many? Because I did provide you with the codes. How many have the codes and are going out there and getting the physics book? Or maybe I'll say it a different way, or plan to go out there and get the physics book if you haven't yet. Okay, and some of you are still thinking about whether you will do that or not. Wouldn't be a bad thing because, you paid for it and I gave you the codes. So, we should be good with that. And this way, some of these things and some additional examples and reading are there. Okay, Linda, thank you. I'm going to close that. And let's just, and I can still advance the slide, so that's good. Now, Linda, I'm going to turn this back over to you. Maybe a little bit, or maybe we'll do this together. But what we're going to do is do a couple of problems. We're going to do this problem 34. Is that 34 or 54? 54. We're going to do this problem 54. And we're also going to do the problem called 55, that was a dislocated shoulder. I will tell you, I've asked both of these questions on exams before. I've never asked them both on the same exam, but you are going to have a vector problem. So these are the two vector problems that we're going to be talking about tonight. Okay, and then we'll do some other things. So please tune in, then we'll go somewhere else. So I'm going to start with this one about dislocated shoulder. And this has to do with biology. That's what the BIO means. So a patient with a dislocated shoulder is put into a traction apparatus as shown in the picture. So you see, here's the person, their dislocated shoulder, I guess, is up here. And they stretch them out in this way, and they sort of put a handcuff on them, but then they put a tension up here that's at 32 degrees, and a tension down here that's at 32 degrees. So there's two tensions pulling on this person in the same plane. So that is the picture, okay? And that's the treatment that they have. So the pulls, vector A and vector B, have equal magnitudes. And by the way, that just makes sense because if this person's shoulder is dislocated, you want to be pulling it out this way in this direction. And you don't want to be, messing it up further by having one of these pulls be stronger than the other. So they have equal magnitudes and must combine to produce an outward traction force of 5.6 newtons on the patient's arm. How large should these pulls be? Okay, so you see, we want to know what's the magnitude of these two pulls. Now, I'm not apologizing for it. This is the book and so on and so forth, and this is the way a little bit physics is. Later on, we're going to talk about force, and we're going to talk about what a newton actually is. All you know now is that's the unit of force, and that's what's being pulled out, and the combined is going to be 5.6 newtons. So, and Linda, I think you said I can write on this. So I'm going to try that again.
You can.
Okay, so this is 5. And Linda, you're going to do calculator things, or if not calculator things, you're going to do Excel, and you may choose to do both, and that's totally up to you. Okay, so the net that we want to have happening here is, God, that's a good 5, is 5.6 newtons. But, and so this is the direction that you need to have, that 5.6 newtons. But you see, these things are equally balanced. And so half of 5.6 is 2.8. I was this morning, Linda, I was working with a student on Zoom, because that's where I do the office hours. And I was really very bad with this, and I think Collaborate might actually have a better thing here. The bottom one is also 2.8. Maybe I'm better at night, I don't know. Newton's this way. Okay. Now, what we're supposed to do is, actually, I don't like what I did. I need to erase that. It wasn't the way, oh, thank you. How'd you do that? Or did
I didn't do anything. I think somebody hit the erase button.
Okay, I must have done, oh, maybe that clears the whole thing. Okay, that's good. Okay, so now I'm going to go back and do this again because I was not explaining that well. So this is 5.6 going this way. And the reason I had to erase it was I actually was screwing it up because since it's 5.6, that means I'm going to get 2.8 from the top constraint. So this is 2.8 going down along here, 2.8, and you get another 2.8 from the bottom one. I'm going to pause for a second here, and then I'm pausing for a second just to see, are there any questions, or is everybody okay with that so far, what I've said? They're saying, some people are saying okay, and Sid, they may have a question. Go ahead.
All good.
Why are you doing that? Like, why would you have to split it in two? And why does the 5.6? Why do you put the 5.6? Like, why is why?
And I'm not being rude when I say that's the problem tells me to, but let's go back and see why that is.
Okay.
Okay. So this is a patient with a dislocated shoulder is put into a traction apparatus as shown in the picture. Now this is the directions for how the traction apparatus works. Pulls going in direction A, vector A and vector B are to have equal magnitudes. That means the pull going here, the pull going here is the same. Some doctor said do it this way, so the nurse fixed it up this way. Okay?
Okay.
But the problem goes on. But when you do the vector sum of vector A going up like this and vector B going down like this, the sum is supposed to be 5.6 going right here, straight out.
Okay.
And what I'm saying is, since these are equal pulls, half of the contribution is coming from vector A and the other half is coming from vector B.
Okay.
And they ask, what is the, how large should these pulls be? And the units have to be newtons. Now there's a picture, and I kind of did that for a while, but let's just make it into a problem then. It's like this. A is going out like this. That's the unknown magnitude. And we know the direction is 32 degrees. And we know that this side down here, this guy, is 2.8. Now this problem by now should start be looking a little familiar because you're saying, oh, I know the adjacent, I know the angle, what I don't know is the magnitude of A. And by the way, by the problem, the magnitude of A and the magnitude of B are the same. So we can answer the problem that way. Now I'm just going over here, and Linda, I'm about ready to turn this over to you, but here's what I'm going to say. 2.8 divided by magnitude of vector A is equal to some trig function. I want everybody to think about what that is, and I'm going to write it down, and this is the cosine of 32 degrees. I want to pause just for a minute before I turn it over to Linda. Does everybody understand what I did and why I did it? Or do you have questions about that? Okay. Oh, okay, good. Thank you, Paula. That is good. So Linda, I'm going to turn that over to you now. And you can either do it with a calculator, which might not be a bad thing just because we have that, that radians controversy that's sitting out there. Or maybe you can do it to Excel. I'm not going to tell you what to do. Go ahead, Linda, you've got the ball.
Yeah, so I'm just going to use the calculator. Before I do that, though, then I am going to rearrange this a little bit algebraically. So if I'm solving for A, then I actually want to divide both sides by the cosine of 32 degrees and multiply both sides by A. That way I have A equals 2.8 divided by cosine of 32 degrees. So my pencil is not working, but I will show you on the calculator. No, that's just my pen not working.
Okay. All right.
But that's fine.
Tell you what, I'm going to help you out with that. Yeah,
okay.
You want to help me out? Okay, so here's what Linda said. You see here we got this 2.8 over A is equal to cosine 32 degrees over 1. Okay, I'll try to write this up here. Okay, so that means 2.8 over A is equal to cosine 32. Then she said, well, and this is cosine 32 over 1. So we could cross multiply and solve for A. And if you did all that, what you would get is that A is equal to, and it is going to be, let's see, 2.8 rather. Over cosine of 32. Again, I hope there's no questions on that. If there are, you should be asking though. Okay, now Linda, go to the calculator screen or whatever you want to do.
Okay. So now to type this into my calculator, then I'm doing 2.8 and then dividing that by the cosine of 32 degrees. Now, if you remember from last time, then we have to type in the angle first. So 32. And then under trigonometry, I can hit cosine. So what it's giving me right now is actually just the cosine of 32 degrees. I still have to hit the equal sign to get what all of this is. So my answer is about 3.3. And this would be newtons in this case. Any questions on that?
Okay, so that means that you have to be pulling at 3.2 off in that direction at 32 and 3.3 at the other direction at 32 degrees in order to get the desired 5.6. And the reason that happens is because you're pulling at an angle so you don't get the full force. Okay, and again, I did ask this on a test once upon a time. So I do ask vector problems. They're not all vector problems, but some of them might be. So there is one. Linda, just for, I don't know, variation's sake, I'm going to read it, but then I'm going to ask you to give number 54 a go, if you don't mind. Okay?
Okay.
So a sailor in a small sailboat encounters shifting winds. Sailor is a she in this case, sails 2 kilometers east. And again, we'll talk about more about what kilometers are and things like that tonight, but 2 kilometers east. And then 3.5 kilometers southeast. And southeast is, let's see, I'm going to try that again. Southeast is smack dab in the middle of south and east, and that's why there's that 45-degree line there. See, this is, it's here you can see north is up, south is down, east is this way, and west is that way. So southeast would be smack dab in the middle of there. Okay, So that's 45 degrees. So here's the story so far. She goes 2 kilometers this way, and then she goes this way, an additional 3.5 kilometers, and then an additional distance in an unknown direction. See, they're not telling you what that direction is that she's going down there. And let's see. Her final position is 5.8 kilometers directly east of her starting point. So you see, she's going to land right here. So she starts here, but she goes down here, and then she goes up here. And what we're really trying to find out is what is the magnitude and bearing of this third leg. So that's the direction that she has to go, and it's that. And Linda, are you comfortable just taking it from there?
Sure.
Okay.
So
here we go.
let's see. So first of all, that 2 kilometers that we're looking at in the beginning isn't going to affect going up or down any, right? So instead, I'm going to kind of cut it off here and call that 3.8. Is everyone cool with that?
Yep.
Okay. So then I need to figure out. So I had the 5.8 kilometers that we started with, and I just subtracted 2 from that.
Okay.
Okay. So then I'm going to figure out what my components of this first triangle are, and I'm making my reference triangle onto my x-axis, or I guess in this case up. So in this case, our angle is 45 degrees, and we have a hypotenuse of 3.5, right? So then my cosine of 45 degrees is going to equal my adjacent side, so I'll call this x, over 3.5. And then my y, so let me label these for you guys. That is going to be my sine of 45 equals y over 3.5. Is that okay? Sydney, what's up?
How do you know, like, how to set up the problems? Like, not the sine and the cosine, but like, how do you know to put cosine 45 equals x over 35? Like, how do you know to do that?
So we're given the hypotenuse. And because cosine is adjacent over hypotenuse, then that's how I'm getting the cosine of 45 degrees equals x over 3.5.
Okay. All right. I don't really, I don't understand it. So I guess I'll have to come to tutoring because it's confusing me. So sorry.
Well, where am I losing you?
I don't understand why do you have to do sine 45 equals x over 35? Like, is that?
Yeah, so sines and cosines and tangents are basically just functions that describe the ratio of the sides when you have a triangle.
Okay.
So all it's saying is whatever this proportion is equal to whatever the proportion of the sides is.
I'm going to leap in and say something additional to what Linda's saying. And Linda didn't say anything wrong. But you see, Linda has worked problems like this before. Okay? And this is not an easy problem. In fact, as I look at this, I think this problem is harder than the one about the dislocated shoulder because you have to think a lot more in setting this up. So you see, Linda has worked this problem before. You're going to see, oh, it was a good idea to split up this with x and y with that perpendicular and things like that. But it's not obvious, although if you're doing another problem like this after seeing this one, you might say, oh, that's what I can do. But this is a word problem. It's a little bit harder to get at that. What you should, I think, they'll be able to do, or what I hope everyone is comfortable is, what did Linda do, not how did she know to do it? Because that comes from her experience, and you're having some of that experience right now as she's working the problem with us. I don't know if that helped or not, but now I'm shutting up. Linda, go ahead.
So just so none of this gets erased, then I'm going to plug this in on the calculator without sharing my screen. So first I'm solving for x, and to do that, then I'm doing the cosine of 45 degrees. So just in my calculator, then I'm typing 45. I'm going under trig, hitting cosine, and then multiplying that by 3.5. And when I hit enter, then I get 2.4748 and change. So I'm just going to call that 2.47. Yeah, the calculator is just the one that is on my computer.
That's what we
So
did
you'll have
on
access to that.
on the midterm, yeah.
So then very similarly, I'm going to do almost the exact same thing to solve for y. So in this case, I hit 45. I'm going under trigonometry, hitting sine, and then multiplying that by 3.5. 3.5. So, and I end up with the exact same number. So y is also 2.47. So if I'm thinking about what's happening here, then I know all of my horizontal shifts have to add up to be originally 5.8, right? Now I already got rid of the 2 from the first leg of our journey. Now in the second leg of our journey, then we have the 2.47 that we traveled. So in my calculator, then I'm doing 3.8 minus 2.47. So 3.8 minus 2.47, and that gives me 1.33. So I'm going to draw a new triangle that kind of represents the last leg of our journey. And my x in this case was 1.33. So then my y, well, because we went down before by 2.47, and we end up exactly east, then I need to go up another 2.47, right? So just like how before we would have gotten a negative 2.47, then this is going to be a positive 2.47. And I say before it was negative because this is actually going down, right? Any questions on that?
So one is negative and one is positive?
Yeah, that's why we end up exactly east from where we started.
Hey, Linda, can you show them where theta is on the drawing with the boat on it?
So theta would be right here.
Okay, good. Thank you.
So I'm putting that in orange so it's a little bit easier for people to see.
So your purple triangle that you drew, that one is inverted from the problem then?
Yes, this purple
Okay.
triangle up here is the third leg.
Okay, got it. Thank you.
Okay, so I need to figure out what my magnitude and what my direction are. So first I'm going to start with the direction. So to do that, then I can do my inverse tangent. So tangent is opposite over adjacent. So my opposite side is this 2.47. And adjacent is 1.33. So I'm going to plug that into my calculator. So first I'm doing the 2.47, and I'm dividing that by 1.33. And then from there, then I'm going under trigonometry, and I'm hitting second to get the inverse trig functions. So then I'm hitting inverse tangent. The tangent with the little -1 is the exponent. And I get 61.699, so I'm going to round that to be 61.7. And this would be going northeast. And I know that just because of this picture. So then the last thing I have to do is figure out the magnitude. So in this case, that's the same thing as just figuring out the hypotenuse. So to do that, then I'm doing 1.33, and I'm squaring that. And then I'm adding to that 2.47 being squared. So that gives me 6.1 and change. And then I'm taking the square root of all of that. So when I add those together, I actually get 7.8698. Then I hit the square root button, and I get 2.8053 and change. So that's about 2.8. And this is in kilometers. Any questions on anything that I did? So you have two answers because they're asking for the magnitude and the direction. So the magnitude would be 2.8 kilometers, and you're going 61.7 degrees northeast.
Okay, thank you, Linda, and thanks everybody for your questions. It was good to ask questions. It's always good to ask questions. You might think, oh, good, I'm never going to see vectors again. That's not really true. A lot of things are vectors in this physics class, but now we've at least practiced vectors a little bit. So now I'm going to advance the slide, and we're going to talk just a little bit about scientific notation and powers of 10. You can see my cursor. No, you can't, but now you can. Okay. In physics, we frequently encounter very large and very small numbers, and you do in ultrasound as well. So it's important to use significant digits, and we'll talk a little bit about those, not a lot, a little bit about those, but we address this using scientific notation. And so you see, here's what we do. Scientific notation in which a quantity is expressed as a decimal number with one digit to the left of the decimal point. Now that really is like important there, because that's part of the definition of something being in scientific notation. So one of the things you need is one decimal to the left of the decimal point. That's exactly one decimal to the left of the decimal point. And then we multiply that by an appropriate number, or by an appropriate power of 10. That ends up moving the decimal point, because we live in the decimal system, one decimal place. So if the power of 10 is positive, is the number of places the decimal point is moved to the right. So if it's positive, you move to the right to obtain the fully written out number. For example, 6.3 times 10 to the fourth is, I will try to do it down here. I think I have a pencil, don't I? Okay, so this is 6.3 times 10 to the fourth. Since the 4 is a positive exponent, I'm going to move the decimal point 4 places to the right. Everybody watch this though. See, the decimal point originally was here. I'm using that little caret just as a placeholder for that. Now I move 4 places, so I go 1, 2, 3, and 4. And so what happens is that 6.3 times 10 to the fourth is 63,000. If the power of 10 is negative, and you might want to think back to that powers of 10 video, it is the number of decimal places moved to the left. Okay, so we've got another example here. This is 6. I just erase that, that's gone, right?
Yeah.
Okay, good. That's actually, if you know how to do that, that's convenient, I suppose. Okay, so let's do this one then. This is 6. I need to get my pencil again. So this is 6.56 times, this is 10 to the minus 3. Now, since this is negative, that means what I'm going to do is move it 3 places to the left. Okay, so my number is 6. This is where the decimal point was, 56. Now I'm moving it 3 places. So going there is 1, 2, and 3. So there's where the decimal point lives. And a lot of times in medical applications, they really want you to put that 0 there so people don't just get confused. They know where the decimal point is. But anyway, you can see that here it is up here. It is there. So that is how you do this. Most calculators have keys for expressing a number, either decimal or scientific notation. I'm not sure about Linda's calculator, but we're going to just do a problem or two. So let's go ahead. And here's an example of it. And by the way, the student this morning also that I was working with was asking, well, how much do we really need to know about exponents? Well, quite a bit. Because look, we're multiplying these two numbers together, 8.43 times 10.8 and 2.21 times 10 to the minus 5. Multiplication is commutative, so I know here I have 10 to the 8th. This is the 10 to the 8th right there. And here I have 10 to the minus 5. When you have the same base and you multiply the exponents, it's going to be 10 to the 3 because you add those exponents. And 8 plus negative 5 is 3. And then we're going to multiply these numbers because now we already multiplied the powers of 10. So this is 8.43 times 2.21. You use a calculator. And when you do that calculation, and by the way, they're probably rounding this number off here, I imagine. This is 18.6 times 10 to the 3. This really is not in scientific notation because I have 2 places to the left of the decimal point. So I have to move it over. And when you do that, what will happen is it's going to be 1.86 times 10 to the 4th. So that's what we're going to have there. Now down here is another calculation, and now you have 5.6 times 10 to the minus 3 divided by 2.8 times 10 to the minus 6. This is what I told the student this morning. You got to be able to do problems like this. You don't have to be the world's greatest expert on exponents and doing fancy exponent things, but you have to be able to do this. So I'm looking at just this part. This is 10 to the minus 3 divided by 10 to the minus 6. When you divide these, it's going to be 10 to the minus 3, and then it's going to be minus a minus 6. So minus a minus 6, they're showing that over here. But minus a minus 6 is going to be plus 6. So that's also going to be 10 cubed. And then you're going to take 5.6 over 2.8, which is exactly 2. So the answer to this problem is 2 times 10 cubed. Okay. Now, when you're adding, subtracting, multiplying, or dividing, keep the proper number of significant digits. We'll talk about that later. And that's how that will work. Okay, so here are 2 problems. And Linda, you want to give, well, there are 4 problems. Linda, why don't you do 5, 6, well, no, Linda, would you mind doing them all? Go ahead.
Sure. So for the first one, then let's see. I have 475,000. So currently my decimal is after that last 0. So let's see how many places I have to move it. So only one number is in front of my decimal place. So that would be moved once, twice, 3 times, 4 times, and 5 times. Puts me right there. So this is just going to be 4.75 times 10 to the what was that? 1, 2, 3, 4, 5 times. So that would be your answer for the first one. Any questions on that?
You must be good at this. That's good. Oh,
So it would not be -5. I know it can get kind of confusing on which way you're moving, left or right. It's easier for me, at least, to think of, is this making the number bigger or is it making the number smaller? So if you have a negative exponent, then it means the actual number was smaller. If you have a positive exponent, then the actual number was bigger. So in this case, because I started out with such a big number, then I should have a positive number for my exponent.
I think you made people happy, Linda. Go ahead to 6 if you will.
Okay, so in this case, I have 0.00000472. So let's see how many places I'm moving my decimal. That would be 1, 2, 3, 4, 5, 6. So I know it's going to be times 10 to the some kind of 6, right? And I know that my number here is 4.72.
Linda, why don't you poll them on that? Is that 6 negative or positive?
Okay.
And please vote. This gives Linda an idea and me an idea of how you're doing with this. Negative or positive? We did pretty well, Linda. You did pretty well. So
I think so.
yeah.
This is definitely a -6 because my original number was much, much smaller, right? Okay. So then for number 7, then I have 123 times 10 to the -6. Now I'm going to ignore that 10 to the -6 for a moment. How would we write 123 in scientific notation? Well, in this case, my decimal is after that 3. So I would need to move this twice over, right? So this would be 1.23 times 10 squared. Now I do still have that times 10 to the -6, but now I can just combine my exponents. So 2 plus a -6 gives me a -4. So this would just be 1.23. That is a 1, not a 7, times 10 to the -4th power. Any questions on that? Okay. So then last but not least, I'm going to clear this out so we can do the last problem. So if I have 8.3 times 10 to the 5th over 7.8 times 10 squared, I'm going to split this up into 2 separate problems. So this is going to be 8.3 over 7.8 times 10 to the 5th over 10 squared. So in my handy dandy calculator, then I'm going to do 8.3 divided by 7.8, and I get about 1.064. And then from here, I'm just using my rule of exponents. So 5 minus 2 gives me 3. So this would be times 10 to the 3rd.
Questions?
How did you get the 1.064?
I just typed that into a calculator. 8.3 divided by 7.8.
Oh, okay.
Now, if I didn't get a number where there is only one number to the left of the decimal place, so just that one, then I would have to rewrite that into scientific notation as well, just like how we did number 7 with the 123. Any other questions?
Okay, good work. And as I told my student this morning, these are the kind of exponents you're going to have to do. It's not doing a whole bunch of complicated things like you may have done in algebra, but these have to be done right, and you're going to be plugging numbers into equations. And so, this is, some bread and butter that you do need to be able to do at this level. Okay, let's move on then. Here we're solving equations. Linda, I'm watching what time it is and everything else. We are going to be solving equations, but I don't know if we really want to just review that right now or not. I think we'll review this in context, so I'm just skipping a few things. This was the algebra review. But we are going to do something here with this. So this is called, we're going to talk about things being directly related and inversely related and so on and so forth. And directly related is the same thing as being directly proportional. Now, I will tell you, folks, that I have looked at your ultrasound textbooks. I've also looked at the ultrasound certification exams and things like that. This is something you need to know. Now, we're going to actually do a bunch of calculations here. A lot of times they just say, oh, the pressure is directly related to something, or the pressure is inversely related to the volume, or stuff like that. They'll just use those words and they'll ask qualitative questions. We're doing quantitative questions. If you can do quantitative questions, you can do qualitative questions. Okay, so now what does this mean? When you see this word directly related, or directly proportional, that means that y, so we say x is directly related to y. That says that y is equal to a constant times x. Now that means this is like a physical law. So that constant is always there, and it's always the same. And so, for example, I think it's a good example. If Linda and I pulled into the gas station and she filled up her big Hummer with 30 gallons of gas, and it cost her $60, and I filled up my dinky Honda with 10 gallons of gas, you can tell me what the relationship is, and that's this constant of proportionality. We're going to do some examples of this in a bit. But that's what it means when we say direct relationship. And that means that things go 0, 0, and it's a slope like this, so it's a line. The slope can be positive, it could be negative, it could be 0, and it could even be an undefined slope. But we also have things that are inverse proportions. What this means is if x and y are inversely proportional, that means that y is equal to a constant k over x. Now, the only way you know to use those different equations is the word inverse. Okay, so we get this, we find out what k is, and we solve it, and it talks about the graph here. Now, we don't have just direct and inverse, though. We have two other examples, I think. We talk about inverse squares a lot, and this will happen frequently. So inverse squares look like this whenever we find that word. And we are going to run across this. Linda will remind me to point back to this lecture whenever we get there, but we're going to find out that the intensity is inversely proportional to the square of the radius, or the distance from the point source. So this is going to be k, but this is inverse square proportion, so we're going to have x squared here. And that's the same thing. Here's what I said. Okay, that's just what I said again. Okay, let's go ahead and do some problems here. So here are two problems I'm going to read. And Linda, if you're comfortable taking over with these, I'm just going to read the first one, 21. I'm going to ask you to perhaps work it. And then I'm going to read 23 and ask you to work it that way. Or we could do it the other way about. I don't care. Why don't we do it this way, just since that way we won't have to haggle about it. Okay, so here's 21. I'm going to read it, and then Linda will work it. For a sound coming from a point source, the amplitude of sound is inversely proportional, there's a key word, to the distance. Now, inversely proportional means that, so the amplitude is inversely proportional to the distance. So the amplitude is equal to sum, capital K, over the distance, because that's what inversely proportional means. Okay, so that is good. Now, if a displacement amplitude of an air molecule is 4.8 times 10 to the minus 6 meters, that means the amplitude, that's substituting here. So this is 4 times 10 to the minus 6 meters. That's a tiny number. And it was 1 meter, so D is 1, so this is equal to, the denominator is 1. And that was 1 meter. Okay, so we can figure out what K is. Now, so Linda, I'm going to ask you to take this, but then they say, you see, we'll figure out what K is, but then Linda's going to find out what would be the displacement of the same sound when the distance increases to 4 meters. Now notice that Linda is going to treat these units very carefully, because you have to treat units carefully. Go ahead, Linda.
I mean, you've done like half the problem for me.
You want me to finish it?
So, I can finish it.
Okay.
So, to get K by itself, then I'll just be multiplying both sides by 1 meter. So, in this case, that doesn't really do anything. So, K is just going to be 4.8 times 10 to the negative 6th. So then I'm plugging
what are
that.
the units, Linda?
The units. Let's
Meters
see.
times meter is?
Meter squared.
Yes. You see, that's important, guys, and that's one of the differences in physics than, it's not really different, but I mean, units are really important. So that's meter squared. And what you're going to find out is these constants, even though they're constants, they have units with them, and units are important, and we're going to do dimensional analysis and stuff later. That is what K is. So now Linda can actually write that equation. Yes, Josh?
Why would that be meter squared?
I will tell you. Okay, because here, wait, let me find my pointer. Okay, that's meter squared because meters times meters. This is meters to the 1. That's meters to the 1. So that's meters squared.
Okay, got it. Thank you.
Okay, great. All right. So Linda, and Linda, if you just write down or memorize what K is, you could probably erase this and have some more real estate to work right on the slide.
I don't think it'll take too much room.
Okay, go ahead.
So they're telling me what would the displacement amplitude of the same sound when the distance increases to 4 meters. So in this case, all I'm doing is plugging in 4 for the distance. So A equals 4.8 times 10 to the negative 6th meters squared divided by 4 meters. So in this case, I can just divide my 4.8 by 4, and that's going to give me 1.2. And one of my meters will cancel. So 1.2 times 10 to the negative 6th meters.
Okay. Well done on that problem. Maybe we do want to, in fact, I will erase this and I'm going to read the next problem. There we go. Now this one. Let's see. The force of gravity on an object varies inversely as the square of the distance from the center of the Earth. Now, it's important that, when you're reading these things, it's not like reading the sports page. These words have a lot of meaning in them. Okay, So that's inversely as the square of the distance from the center of the Earth. And that was the force varies inversely as this. And that's actually how it does vary. That is the physical law. So it says, find the force of gravity on an astronaut when he is at a height of 6,000 kilometers from the surface of the Earth if he weighs 700 newtons when he is on the surface of the Earth. The radius of the Earth is 6.38 times 10 to the 6th meters. Okay. And so, and they parenthetically say if an astronaut is in orbit, he will float weightlessly, but gravity still acts on him and his spaceship appear weightless because they are falling freely in their orbit around the Earth. You may have to think about that for a while. Okay, so now what I'm going to do is, okay, so to get my, Linda, you have these numbers memorized, yes?
Not quite.
Okay.
So
Right, I guess I will just try to do it here. I'm going to go ahead and talk through this. I was feeling I was texting you more than maybe I should. But anyway, here what we're doing is, in fact, I'm going to just draw a circle. Now pretend that that is a circle, and pretend this is the Earth. So you see, we know the radius of the Earth because they told us in the problem what that was. And the astronaut on the surface of the Earth weighs 700 newtons. So that's the force of gravity when he's on the surface. Now what we're saying is at a height of 6,000 kilometers. And by the way, this was meters. This is actually a good problem. So this is, so the R is equal to 6.38 times 10 to the 6th, 10 to the 6th, and that is meters. Now he is going to be an additional 6,000. This isn't meters anymore. This is kilometers, or K times M. Okay? So now what we need to do is we need to, and the question that was being asked is, determine the force of gravity on him when he is at 6,000 kilometers from the surface of the Earth. Okay. So now what I'm going to do is, Linda, the only number I'm asking you to write down on a sheet of paper or something, because I'm going to ask you about it, is this number right here. Okay, and that's meters. All right. And now I'm going.
I didn't see you point to anything.
Thing I tried to like circle or something.
Okay.
All right, now, and is this the, that's not the whiteboard. Where's the whiteboard?
Let me share one.
Go ahead, please. Thank you. Okay, here we go. Now we're doing some things. Now, here's what we know. We know that F, the force, is equal to a constant times the square of the distance from the center of the Earth. You see, this is an inverse square law. Okay, so now we know that, in fact, you can't just erase that, can I? I have to erase the whole thing. I'm not going to do that, so I'm going to just go over here. So we know that 700, this is newtons, is equal to K over, this was at the surface of the Earth. So this is going to be 6.38, Linda?
It was 6.38 times 10 to the 6th.
Yeah, not bad for an old man, huh? Okay, so this is 10 to the 6th. That was meters. Okay, but then they ask, what does a person weigh? So that is an unknown F And that's equal to, I'm doing this a little bit fancier, but that's okay. And this is K over. And now what we have to have is we have to have the distance. By the way, this was the distance supposed to be squared, because the formula had it squared. So now I'm going to put this number down here. This is going to be 6.38 times 10 to the 6th. And I'm going to put meters there. But you see, I have to add this because you see we were here. This was the radius of the Earth. Then we're going up another 6,000, and this is kilometers. Now you see those numbers don't really match in units, do they? So we have to fix that. And kilometers is 1,000 meters. So what we're going to do is we're going to change everything to meters. And so I'm going to have 3 more zeros here to change this to meters. So this is going to be plus, what's that number, plus, and this is going to be 6. I already got 3. I'm going to put 3 more. And that is meters. And that is all going to be squared. So now what I can do is I can divide one equation by the other, and the k's will cancel. So what I'm going to have is 700 over F. Oh, I didn't leave myself enough room, but I'll try it anyway. This is equal to, now I'm taking now 1 over this business, divided by 1 over this business. That puts this one on top. So I'm going to have 6, 0, 0. How many I got? 1, 2, 3, 4, 5, 6. 6, 1, 2, 3, 4, 5, 6, plus 6.38, and that is whole squared, divided by, and this is going to be 6.38 times 10 to the 6th, whole squared. Then I'm going to have to cross multiply, because you see I got this one over this one is equal to this one over this one. So I cross multiply and I'm solving for F. So what will happen is I will take 700 times this denominator is equal to F times this denominator. And that means the final answer is going to be 700 times 6. Sounds like Linda's using a calculator. That would be good. 6.38 times 10 to the 6th. That's whole squared. That's a 10 to the 6th. Whole squared. So 700 times that. And I'm going to be then dividing this by, this is going to be 6 with 6 zeros. Plus 6.38 I wish we had a chalkboard, actually. That would be better than this. Times 10 to the 6th. That denominator is whole squared. So quite a bit of calculation there. And but we did change everything to meters, okay? And so we're going to end up with newtons just as our unit. Okay, so and Linda, what did we get?
185.9.
Okay, now you see that actually makes sense because on the surface of the Earth, he's closer to the center of gravity, and so that's 700 newtons, but then he goes up and it was less than 200 newtons that he weighed at the other point. I'm going to pause for a second, and Linda, well, no, let's just, are there questions or is that good?
So if this problem was a little bit hard to follow with all the exponents and things, then it may be helpful to work through it on your own with writing everything out without the scientific notation and see if that makes a little bit more sense.
Okay. Now I do watch the clock for you, free of charge. And Linda, let's go back to the slideshow. Let
Okay.
you figure that out. I do know what time it is, but we're doing fine. Time. And thank you, Linda, for doing this. I just can erase that. Yes, I can do that. Okay. All right, so there we go, and I'm advancing a slide. Okay. Now, I'm going to be relieved that we're not doing logarithms today. We will later, but we're going to just do those in context. And we're going to talk about areas and volumes in context, but they also just get brought up every so often. This is mostly plugging in numbers, but here's a better problem that I'm going to pause, put here. And you know what? By the way, no one got hurt with low stakes assessments. Everybody remember that? Okay. I think we're going to make this into a low stakes assessment. And that means, Linda, you're going to set up a place for people to upload a PDF and place for people to put answers.
Okay.
What's today? Today is Tuesday. When do you think this ought to be due, Linda? I don't really care.
So Monday night next week?
Okay, so Linda says, so we'll do this Monday night, and I'll put this there, but it's going to be this problem, and I'm going to read it for you right now. I have 3 minutes to read it. So if a brass washer has an outside diameter of that many centimeters with a hole of, and Linda said Monday, that means we get to meet one more time on this, so that'll be good. With a hole of diameter that big, 1.25 centimeters, and that's how thick it is. You see the figure. The dividity of brass, they tell you, if you put the washer on a laboratory scale, what will it weigh in terms of grams? We'll say more about this later. Again, the way physics works is a lot of times they just make things up along the way, and this is made up here. It says, recall that the density is mass divided by volume. Now, why are you supposed to know that? I don't know, but they felt you were. We actually study that in a later chapter, okay? Now, so one of the things that you're going to be doing is you're going to be doing volume problems. You have density equals mass times volume. We'll talk more about this next time. But so let's see, this was that number 20. Okay. We're almost finished with chapter 1. We got a couple of more things that we're going to do here, and so we'll do some of this stuff next time. We'll talk about dimensional analysis. We'll talk about prefixes. We already actually started talking about prefixes. You remember we were talking about kilo. Here is kilo down here. That is 10 to the 3. Now you will have these tables, but that's the way physics is. You have all those units that are there. So that's what we have. And we do have a question. Go ahead, Jessica.
For the homework, you said to upload a PDF. Would that just be uploading our work? Whatever.
And I think Linda's going to make an answer sheet there in the assessment tab for that also. Jessica, did I answer your question?
Kind of. So do we upload our work, like show how we got the answer in the PDF?
I don't think you do that. But
Okay.
the other thing is there's going to be an answer sheet there, and I don't think the answer is 5, but if it was 5, you could tell me 5, and also you should tell me what the units are as well. Okay.
Perfect. Thank you.
All right, excellent. And now, is this class well planned or what? Time is precious. Each day must count. Do the math. It will make you strong. I have office hours at 7:30. Thank you, Linda. And I think we're good to go.
Okay. Molly, my hours for this GSG are, let's see, 5 to 6 on Tuesdays and Thursdays. But I also work Monday from, let's see, 11 to 3 in the daily drop-in, as well as Wednesday from 10 to 3 and Thursday from 11 to 3. So plenty of time where you can come see me.
Okay, we're out of here. I'm going to stop recording.
I have a question.
Go ahead and ask your question. You're still here.
How do I get to the GSG?